Hello, budding mathematicians! Welcome to this video lecture, number 6 in our series. This one teaches the method of separation of variables in the solution of PDEs. You may remember a method with the same name from an earlier discussion of ODEs. However, you will find that the methods of solutions of PDEs tend to differ from their simple, ordinary cousins. For example, when we were studying ordinary differential equations, it was often the goal to find a general solution of a differential equation, often constructed with a finite number of particular solutions. However, when dealing with a PDE, it is often not feasible or even useful to look for a general solution explicitly. Instead, it is more useful to seek particular solutions of PDEs. Oftentimes, we will discover an infinite family of such solutions by one method or another. Families of solutions can then be later accepted or discarded depending on what kinds of auxiliary boundary or initial conditions we apply to the problem. And another thing, while they were normally general methods of solution for large classes of ODEs, we will also see that this is much less the case for PDEs. The solutions of some of the simplest and most fundamental PDEs were found by trial and error by mathematicians over the last 3 or 4 centuries. And of course, most PDEs don't have closed-form solutions at all and must be treated numerically. That being said, there are some tried and true methods which do come in handy when you come across a PDE in the wild. One of these involves the concept of a separable function. For a function of 2 or more independent variables, we say that the function is separable if we can write it as a product of functions, each of a single one of the independent variables. Given a second-order linear PDE, we say that the equation is separable if its solution is separable, namely, if it can be written as a product of a function big X of x with the function big Y of y. One may then ask, under what general conditions is a PDE separable? The answer is kind of disappointing. It's the same as the definition. It is separable if it has a solution that is separable. The rule of thumb here is, if it works, it works. If you see a PDE that you'd like to solve, try to apply the following method. In some cases, it will work out nicely. In others, not so much. We could begin to apply the method by assuming that the solution is in fact separable. Then we can calculate the partial derivative terms that appear in our PDE. If our solution u is separable, these derivatives will have the present form. We can then plug these derivatives into our original PDE. If all goes according to plan, we should be able to separate the functions in x from those in y. Here we have some function f1 of the big X and its derivatives on the left-hand side, and f2 of the big Y on the right, each independently a function of the independent variables x and y respectively. Then the left-hand side, which varies with x alone, is equal to the right-hand side, which varies with y alone. The only way this is possible is if the quantities on both sides are equal to some constant, which we will call negative lambda. Since f1 and f2 are independently equal to negative lambda, we can rearrange them into 2 differential equations for the big X and the big Y. But these will be ordinary differential equations due to the separation of variables. Given that we spent the first half of the semester studying ordinary differential equations, there is a good chance that we should have some idea of how to solve these for the functions x and y. Determining solutions for big X and big Y then determines u, a solution for our PDE. In this example, we are asked to find solutions of this partial differential equation, defined by the second partial derivative of u with respect to x minus 4 times the first partial derivative of u with respect to y equals 0. In order to find a solution, we can assume that the solution, u of x and y, is separable. Then the derivative terms present in our PDE, the second partial derivative with respect to x, and the first with respect to y, have this form. Plugging these into our differential equation and separating variables, you see that we have two terms, one a function of x and one a function of y, both equal to a constant, negative lambda. We see that this results in two separate linear ODEs with constant coefficients, a second order equation in the function x and a first order equation in the function y. These can be directly solved using known methods. There are three possible cases involving the constant lambda. The first, when lambda is equal to 0. The second, when lambda is less than 0, in which case we can say that lambda is equal to negative alpha squared, where alpha is some real number besides 0. And the third case, where lambda is greater than 0, or lambda equals alpha squared. For case 1, with lambda equals 0, the differential equations can both be solved directly by integration. This yields a linear solution for the function x with two constants of integration, and a constant solution of y. Then, for this case, our solution u is an arbitrary linear function in x with two free constant parameters. This is an infinite family of solutions to the PDE in linear form. For case 2, with lambda less than 0, we have these two differential equations for x and y. You should by now be able to immediately recognize and solve these ODEs. Solving the equation for x, we see that the auxiliary equation yields roots of plus or minus 2 alpha. Then x equals c1 e to the 2 alpha x plus c2 e to the negative 2 alpha x. I just noticed that I wrote down 4s in the exponents here. I must be getting cabin fever. Please disregard this obvious error. Similarly, the solution of the first order equation in y is c3 e to the alpha squared y. This then gives us a second form of the solution u to the original partial differential equation. There are those pesky 4s again. Please change them to 2s in your notes. Finally, we solve for the form of the solution in case 3, where lambda is greater than 0. In this case, the auxiliary equations for the equation in x yields imaginary roots, plus or minus 2 alpha I. Then x equals c1 cosine 2 alpha x plus c2 sine 2 alpha x. The equation in y yields another exponential solution, c3 e to the negative alpha squared y. We then have a third form of the solution u to our original partial differential equation. Thanks for watching this video on separable partial differential equations. Please feel free to contact me if you have any questions.